Okay, so just to get started with today's lecture. Uh, so one thing is, it's good to see that some students have started to construct some interesting problems, and see, it doesn't matter whether or not your questions are good or perfect. What matters is you are making an effort, because that is what gets your mental thought process going in the right direction. Where, as I said last time, that you get into the exam paper setter's mindset, how are different ideas created, and then when you actually solve the problems, these all of these thoughts will be helpful to look at different insights in the problems. So I hope everybody keeps doing this. And I mean, this is not just a one-off thing, that the paper which all of you solved, that was the inspiration. We'll be doing lots of problem solving practice all the time. And so anytime we solve a problem, we should automatically think about this, that what can I do to make the problem more generalized, or add some my own twist to the problem. So I mean, it's just about being naturally curious about the mathematics we are doing. So all of these things will come naturally to you. It's just natural that you get into the flow of thinking like this. Okay, so I think you have to keep doing it. Now coming to how, so I would say this is the first proper lecture that we have. So just want to give you some idea about how I am planning to outline this year's program. So as you may know that in October, last week of October, I think is going to be our first Olympiad exam, IOQM. So which means that we are around 3.5 months to prepare for that. And of course, honestly, the subject material is so vast that we cannot cover everything this way. And there is no need to do that also, because last year I already conducted a similar course. So roughly speaking, I would say that I covered 50% of the topics last year, and thankfully all of that is available on YouTube, which is recorded. So what I'll be doing this time is covering the topics which were not covered last year. I'll start there. So particularly number theory was not done at all last year. So first topic I want to start with is number theory, and I'll encourage you to go and watch those YouTube videos which cover other things such as geometry and algebra. Once we finish number theory, we will come back to those topics also. So you'll get a chance to go through all of them with me. But until then, I mean, you don't have to wait for that. If you have time and you are interested to check those videos, you can get a jump start. In fact, what I was going to do was, I mean, those YouTube videos are just recorded the way we have lectures, right? So many times there are long pauses between the videos, because I mean, I give the students some time to think. So maybe for 15-20 minutes, nothing happens in the video. So it's not very fun to watch that way. So I'm going to edit those videos and make it like a more easy to watch, but that will take me some time. Until then, you are free to just go and check my channel and see those videos as they are, like raw content as it is right now. Okay. And along with all of this, I mean, this is the theory part of it, but I think what we also need to spend a good amount of time is problem solving practice. Because I mean, just knowing the theory is not sufficient. As you saw last time, that the question paper that all of us attempted, we knew most of the theory, like at least 70-80% of the theory, I think everybody knew. But the difficulty was how to apply that. So I think we need regular practice for that. And my plan is that every week, or at least once every 2 weeks, I'll keep giving you practice worksheets. So that like 6 to 10 problems which you should try at home. And depending on if we have time, we'll discuss them in the class. But if not, I will give you the hints and solutions, everything. So you can study it on your own. So I mean, basically the way I look at it is pre-RMO level difficulty, something that you should self-study. That is not something I'm going to teach you. The course material we are going to cover is going to be RMO and above from RMO. Okay, so that is how I think we can plan our lectures. Okay, and also just to mention the constructed problem that everybody has submitted so far. So I have some feedback about that also, but I'll need some time to go through it. Few things which I'll note are that, I mean, many cases the problem is constructed very nicely, but the solution which you are writing, sometimes either there are some 1 or 2 cases I found a small flaw in the solution, but in some cases it was not a technical flaw, but just the writing style can be improved. So that is also something which will be important from the once you get to the subjective round. So that is in more and onwards. That is where the writing style starts to matter even more. And the thing is, you cannot hope that right now you will not do any writing and suddenly the day of the exam you will become a very good writer. That is not how it happens. So you have to practice the habit of writing good solutions from the first day itself. Okay. And so any problems that we solve, I would recommend to you that maybe, I mean, trying to write out the solution for every problem will be time consuming, but at least 50% of the problems you can try to write out completely the way you write in the exam. So all the justification given, all the steps are written properly, so that you get into the habit of doing that. And this is an open offer that anytime you write a solution like that and you want me to take a look, you can always send it to me. Okay. So I'll take a look and give you some feedback on where you want to improve your writing style. Okay, so this is like, I expect you to try this effort. I will not go chasing each of you asking that have you submitted a solution. So if you want my feedback, I am always available. Okay, so with that, I think we'll start today's lecture.
So this year would be a PRM or RM, or it would be same as last year?
So no, there will be a stage called IOQM, which will be PRMO plus RMO combined basically. So I think pretty much the same as last. No, in fact, I think last year there was only one exam, so it would not be that way. So we'll have at least two different rounds. One will where pre-RM plus RMO they will be combined, and that will be a purely objective exam like 00 to 99. And then you will have a separate INVO exam, which will be a subjective round. So I think you can find all the details about that on the SBCSC website. I'll just post the link of that on our group so everybody knows what is exact Olympiad calendar for this year. Okay. So just to go over the outline of what number theory comprises of and what we plan to cover. So in fact, I had at some point written very detailed notes about all the number theory properties that are of interest to us. So I'll share this PDF with you at some point, but not before we have covered at least a good amount of course material. And I don't want this to be a ready reference for you so that you don't have to create notes. I think it's a good idea that you create your own notes and organize them the way you think about the subject matter. So that is very important. But in general, just to go over the outline of what are the broad topics within number theory. And I mean, looking at these titles, you may feel that you know most of these ideas, and which is true actually. So we know what are prime numbers, for example. We know what is the Pythagoras theorem and things like that. But what is important is to bring two aspects to mind. First is that there is a certain rigor in the way the theory is constructed, which we have never studied in school so far. I mean, we just introduced that some definition of prime numbers and every number can be factorized. But have we actually tried to prove that every number can be factorized and there is a unique factorization or things like that? So a lot of things which we never did rigorously, which we are going to do in this course, for two reasons. One is just to appreciate how the rigorous development happens in mathematics. And second is that these techniques are all going to be useful in problem solving. But when you write an Olympiad problem, you are expected to follow the same standard of rigor and mathematical logic. So you should be aware of that. And another important aspect of number theory, which is very interesting to me personally, but unfortunately doesn't get covered in Olympiad, is that number theory is actually a very deep subject in mathematics itself. So it goes all the way to the foundation of how mathematical logic works. So there are a lot of interesting sort of deep ramifications of number theory just outside the properties of integers. So once in a while, I would like to talk about that also, because I mean, one of the objectives of this lecture series is not only to prepare you for the Olympiad exams, but to give a general idea of how mathematics looks like. If you some of you are interested in pursuing higher mathematics, maybe masters or higher, then you should get an idea about what is higher mathematics looks like, and that may help you to make suitable choices at the right point of time. Okay. So to begin with, just the basic properties of integers. So how do we construct integers? That is the first question. So if I ask you to define natural numbers, has anybody tried to do that? Like define what is a natural number? Can anybody volunteer a definition?
Can I try?
Yes, go ahead. Arnav.
Sir, the set which contains 1 and contains n plus 1 whenever it contains n.
Okay, the set which contains 1 and what did you say?
And contains n plus 1 whenever it contains n.
Okay, this is a set of natural numbers as according to you. Okay. Anushka, do you have any idea?
It will be the counting number, that is the integers or positive integers, like that excluding 0 and the negative numbers.
Okay, so counting numbers are integers excluding 0 and negative numbers. Okay. Anybody else? Or everybody is satisfied with either of these definitions? Anybody has a problem with these definitions?
Sir, for the second one, I thought we would have to again define what are integers.
Yes, sir.
Yes, sir.
Yes.
So yes, in the second definition, we don't know what is an integer, so we need to define integer. Very fair. But then now in your definition, I need to define what is 1 and what do you mean by n plus 1?
Yes, sir. The operations and the basic ones.
Sorry.
The operations and the
Yeah, we need to define the
real
operation.
numbers.
Right? So, and even what is the meaning of the term 1? When you write 1, what does it mean? So then I guess you have to define 1. Can you define 1 for me?
The multiplicative identity of real number.
Multiplicative. What is multiplicative? What is identity? Can you define
Yes,
multiplicative?
for every real number, a into 1 is a. But then
So to define natural numbers, you need to assume real numbers, is what you are saying. So you see the problem that anytime you try to, this is a general problem, that anytime you try to give a definition, you are going to use some terms. And then you have to ask the question that what is the definition of those terms? And then you have to ask what is the definition of those terms. So seems like this is an unending process. So then how do we define anything? How do we even get started? Seems like we can never define anything because every time we will get the question, something else needs to define. Yes, girl.
So we have to consider something as a basic or means obvious, and based
Okay.
on that, considering that it is true,
Yes.
we develop certain things based on that. We derive certain theorems basically.
Right. Yes. So that's an important observation. In maths, we often call them as undefined terms. So undefined terms are some constructs or some entities that we don't attempt to define at all, and we use them as the starting point, so that we can get started with this process. Otherwise, this will be an infinite loop, right? So we need to have some starting point which we call undefined terms. For example, in geometry, you may already know that we consider things such as point, line, and plane as undefined terms. So we give examples or illustrations that what is a point, what is a line, but we can never give a formal definition of those things. And then given the starting point, we can construct other things in terms of point, line, and plane. Like we can define what is a triangle and so on. So the same thing we have to do in number theory also, that we have to assume some undefined terms. Now the interesting thing is that in mathematics, everybody agrees that there has to be undefined terms, but there is nothing that forces you to say that these have to be our undefined terms. So for us, like naturally, maybe we can say that for us, natural numbers are undefined. Okay? So we just assume that natural numbers are given to us by somebody, and we use that as a starting point. But there can be more expert mathematicians who know how to define natural numbers in terms of something else. So for example, there is a very well-known construction that uses the language of set theory. So a set is undefined. So for somebody, they may use the set as a starting point. And if you give me that set is an undefined object, then I can use the concept of a set to define a natural number. Okay. I'll just show you one illustration of how you can use a set to define a natural number. And this is like, generally speaking, there are multiple ways to do this, but this is just one example. So this is how I define natural numbers. So in fact, I'm going to define natural numbers plus 0. So the union of natural numbers and the 0 set. Okay. So this is how I can define natural numbers. I define 0 as the empty set. Okay. And I define an operation called S, which is a successor, which simply means that the natural number which is going to come after the current one. And in some sense, this is going to be very similar to the definition which Arnav gave, because what I'm going to do is I define 1 as the successor of 0, okay, which is the term which comes after 0. And anytime I want to define a successor, I just wrap the inner object inside one more bracket. So this is nothing but the set which contains the empty set, which may look like a funny object. But this is a set. This is a non-empty set, by the way. This set has one element, and that element is the empty set. Okay. I define 2 as the successor of 1. So what will 2 look like? It is the set that contains the set that contains the empty set. So in this way, the number 10 is nothing but a set which contains the set which contains the set which contains the empty set. Okay, this is a very strange way of defining natural numbers, but it is defining natural numbers, because finally what we call the definition is what we construct, right? As long as what you call natural number and what I call natural number agrees and all the properties agree, then there is no problem with this. Okay. But important to say, I'm just illustrating how some mathematician can use set theory to define natural numbers. I'm not saying that every time we think of natural number, we have to think about it in this way. The point is that some object has to be called undefined. So for us, let us say that natural numbers are the starting point. So we'll say natural numbers are undefined. We'll accept this as a given fact, which means that we accept, along with that, we also have to accept some properties of the natural numbers. Because again, when you try to prove a theorem, you are going to use some other results and so on and so forth. So you need to start with some axioms also. So undefined terms and axioms, these are the starting point of any mathematical development. And just as in geometry, you have undefined terms like point, line, and plane, and you have many axioms in geometry. In the same way, in natural number theory also, we have to have some starting point or axioms. Okay. One such axiom is what is called a well-ordering principle. Have you heard of this term? Anybody?
Yes, sir.
Yes, sir.
What is the statement of the well-ordering principle?
Any non-empty set of non-negative integers has a least element.
Correct. Any non-empty set of non-negative integers has a least element. Can anybody try to write the same thing, not in English but in mathematical notation?
Can I try?
Yes, go ahead.
Sir, we can write the set A is equal to in set curly bracket x1 comma x2 comma dot dot xn, where n is greater than equal to 1. All x are greater than equal to 0.
Okay.
And n belongs to natural number. Xi belong to integers.
Okay.
And n belongs to the natural numbers. I think that would be better if we say n belong to natural numbers instead of saying n greater than equal to 1.
Okay.
So, and here there exists j belong to natural, j belong to natural such that 1 less than equal to j less than equal to n.
Okay.
such that for all k same condition, xj is less than or equal to xk.
So all k in the same range 1 to n, right?
Yes, sir. Less than or equal to xk.
Okay. Does everybody follow what Arnav described here? So A is a set of natural numbers x1, x2, xn, which are all greater than 0 integers. Then there exists some index j, which means that one of these xi or xj is going to be such that xj is smaller than or equal to xk for all k. Anybody else can give a, can you try to make this more concise? See here, you are unnecessarily defining what are the contents of the set A. Can you think of a more concise way to write the same thing? In fact, can you think of a concise way to write the whole first line? That is the first line, all of it, what was it saying? That A is a non-empty set of non-negative integers. So to begin with, let me introduce a notation. So I think all of us know that the capital Z is kind of, I don't know, Cyrillic or different script is used to indicate a set of integers.
Yes.
We can, in our class, we can start to use Z0 to indicate the set of non-negative integers. So how about I can just say that A is a subset of Z0 and A is non-empty.
So can we use W? So you can also use W, right?
Yes, I think some books do use W because to refer to whole numbers, right? That is where the only difficulty in when you try to write that in an exam, I don't know if the examiner knows that W notation. I mean, this is more sort of standard. And even here, like whatever you use, if you want to use W, but writing in the exam, better to make it clear that let Z0 denote the set of non-negative integers or W, anything that is fair. Okay. Yeah, actually, the reason why I'm using this Z0 is that we can easily extend it for different cases. Suppose you want to refer to only the positive integers. Of course, n is one possibility, but you can also write Z plus. Okay. And if you want only negative integers, you can write Z minus. So, I mean, there are ways to extend this notation rather than introduce a new character. Okay. So do you see that this is a much more compact notation that if A is a subset of Z0 and A is either you can say A is not equal to the empty set or you can write simply mod A, the number of elements in A is greater than 0. Both say the same thing that A is non-empty. Then there exists some element n in A such that for all elements in A n less than or equal to n. Okay, so in this, there are two symbols introduced which I don't know if you have seen before. So this is the ulta e is means there exists. So there exists some element of A such that for all m in A, n is smaller than or equal to m. Actually, I'm assuming a lot of set theory notation here. Is everybody comfortable with that? This belongs to a subset, modulus, etc. These are all standard set theory notations, which I hope you have seen somewhere before.
Sir, I have a question.
Yes, go ahead.
Sir, if A is an infinite set, then are we allowed to talk about its modulus?
Yes, you have a fair point. So I guess I cannot use this notation. Actually, the thing is for an infinite set also the modulus does make sense. I mean, what we call an uncountable set. So you will see some books which do refer to it this way. But I mean, to be fair, I mean, or rather to be safe, let's not confuse ourselves. So best to call it this and not this. That's a fair point.
Thank you.
I mean, we are not talked about how do you count the number of elements of an infinite set so far? So we cannot talk about this notation yet. Okay, so this is the well ordering principle, and as I said that we are going to assume that this is given. So we are not going to try to prove the well ordering principle, but we'll use the well ordering principle to prove other things. So we use this as a starting point. So for example, one thing which we can try to prove is induction. So the theory of mathematical induction. So the thing is, mathematical induction is a theorem and it is also problem solving tool. And there is a very subtle difference between these two viewpoints. So first let us look at what is a theorem. So what does mathematical induction entail? That basically given some set S of natural numbers, okay, such that two things are given about this set. That one belongs to the set, and for any k, if k belongs to S, any natural number k, if k belongs to S, then k plus 1 is belong. Then the claim is that S is the set of natural numbers. So what induction is basically saying is that if you need a starting point, so this is what is called a base step. So the chain of events starts at 1, and whenever k is a part of the chain, then k plus 1 is also part of chain. So naturally from 1, 2, 3, 4, 5, 6, all the natural numbers will be covered and everything will belong to this set S. Okay. So I'll give you a few minutes to try and think how we can prove this formally. So how will you prove mathematical induction?
Sir, shouldn't we write 1 is belongs to A, belongs to S, or set 1 is a set of
No.
S?
And the second step also k belongs to.
Belongs to S, yes, correct. I think I got confused between this notation and this. Even here. So try your best to write a mathematical proof of this, and I mean try your best to make sure it is rigorous. So it is not based on only pure observation. That something that we saw last time. I think that problem x1, x2, xn. We observed the pattern, but then we also have to give a proof of why that works. So like a non-mathematical proof of this would be what I just said, that 1 belongs to S, then because that 2 will belong to S, then 3 will belong to S, and continuing in this way, we will get all natural numbers. That is a okay way to explain the induction, but it is not a complete proof. Okay, so how do we get started? What should be the first thing we should think about? I'm sure you have written proofs before, right? So how do you try to prove something? And I see Arnav, Anushka, Garu, only 3-4 students respond. Everybody should try this. If it's wrong also, it's okay, but you need to make an attempt.
If possible, k plus 1 does not belong to S.
Okay, so proof by contradiction or indirect proof, right? We want to prove that the set S has all the natural numbers n. See, if already S has all the natural numbers, then we have done nothing to be proven. So we want to show that if possible, so you said k plus 1, but I would say if possible, let k be some natural number such that k does not belong to S. Okay. Now we have to find some contradiction. So what can be the contradiction here? And see, the only tool that we know so far, the only thing we have covered is well ordering principle. So you may know the saying that if all you have is a hammer, then everything looks like a nail. So if you only have well ordering principle, then you have to use the well ordering principle. It's the very simplest thing that you can do. It's difficult when you know 20 things, then you have to think about, okay, what do I apply now? But you don't, thankfully, you don't know 20 things. You only know one thing. So you have to apply it. So if you want to apply well ordering principle, you need some set. You need some non-empty set of natural numbers, and then that set will have a least element. So here we found one element k, which is not in S. Maybe there are more, right?
Sir, I
Can
think
we
I
consider?
proved
Yes,
it.
Word? Somebody was saying something.
I think I proved it.
Okay, so can you tell me what should be the next step?
Actually, I started a bit differently. I considered the set n minus s.
N minus S. Okay, fine. So yeah, actually I was going to come to the same thing. So if we consider the set of we can call it T, which is the set of so this is the notation which is used sometimes n/s, or more formally it is all the natural numbers such that they don't belong to S. So the complement basically. Okay. So this is the complement of the set S. So these are all the elements which don't belong to S. So if we know that some k does not belong to S, which means that it has to belong to the complement. So are we sure that this complement is non-empty? Because we are doing the
No, sir,
indirect.
yes, sir. We assume that the complement is non-empty.
Correct. So assuming that the complement is non-empty, which we already did here. So therefore, T is non-empty. Therefore, what can we say by well ordering principle?
The T has a least element, say n.
Correct. Such that okay. So T has some least element n such that n is smaller than or equal to m for any other m belonging to T. So in particular, can you tell me which element does not belong to T? The first thing is, can n be equal to 1?
No, sir, since it is given 1 belongs to S.
Yes. So because 1 is given to belong to S, right? So since 1 belongs to S, therefore 1 cannot belong to T. So therefore n is clearly not equal to 1, or in other words, n is greater than 1.
Yes, sir. So n minus 1 will belong to S, but no.
Correct.
N minus 1 will belong to S.
Correct. So n minus 1 cannot belong to T because of this condition. Correct? N minus 1 cannot belong to T. Therefore, n minus 1 has to belong to S. So what can you say if n minus 1 belongs to S? Then usually the second condition, what it says, if any element belongs to S, then the element after that should also belong to S. So therefore, by condition 2,
Sir, I didn't get why 1 should not belong to T.
because it is given 1 belongs to S, right? And S and T are complement sets. So T is all the elements which don't belong to S.
All right, right. Got it.
So by condition 2, N belongs to S, and this is clearly a contradiction because now N belongs to both S and T. So when you get a contradiction, it means that our initial assumption was wrong. So therefore, our assumption that T is non-empty is false. So therefore, T is the empty set and S is the set of the entire natural numbers. QED is I think Italian short form, Latin or Italian, I forgot. Basically means the proof is complete or hence and we are done. Something like that.
Sir, after since 1 belongs to S implies 1 does not belong to T, but I didn't get the next step what you've done.
So here, what is the definition of N? N is the element of T which is smaller than everything else. So if 1 is not in T, then N cannot be clearly 1, right? If N is equal to 1, then it means that 1 belongs to T.
Right. Okay, so we have taken N greater than 1 and then we have written N minus 1 doesn't belong to T.
Yes.
Okay.
N minus 1 doesn't belong to T because of the well-ordered principle. See, if N minus 1 belongs to T, then this condition won't be true, right? N has to be smaller than every other element in T.
Right, right.
So in other words, any element smaller than N cannot be in T.
Right, correct. Got it.
So like if you want to see this visually, what we are saying is that the set S looks something like this. So S clearly contains 1, 2, 3, etc. Suppose S does not contain an element N. So N is not in S, which means that N belongs to T. Then, or rather, N is the smallest number which belongs to T. Therefore, the number before that, N minus 1, has to belong to S. Every number has to be in either T or S. So as soon as the previous number belongs to S, we can use condition 2 and say that the number after N minus 1 should belong to S. So we end up in a situation where N belongs to both S and the complement of S, which is not possible. Okay, does everybody follow this? How we are constructing the rigor in this question? Okay, so this is what we call the normal induction. There is something called a strong induction also, where the second condition is replaced by something else. So here, instead of just saying only saying that K belongs to N, we have a much more stronger assumption that if all the elements of 1, 2 up to K, all of them belong to S, then K plus 1 belongs to S. Okay? So this is slightly stronger version of induction and it is required sometimes. Okay? So this is the theorem of induction, but now we have to see how this becomes a problem solving tool, that how we can use this to solve various problems. So one example was what we did last time. So if you remember, we had that sequence, question, right? Alice plays the game. So there the sequence was something like, I think x0 starts with M and x1 is M plus 10 by 2, etc. So there we said the general term was xt plus 1 is xt plus 10 by 2. And we wanted to find a formula for xt, right? So find the formula for xt. And there were a couple of different approaches. One was, if you remember, I had given you the idea of restore the form, okay, by which we can directly get the answer. But there was another method where you observe some pattern and you guess that this should be the formula. I think the formula was something like n minus 10 by 2 is plus 10, something like this. But there I observed that you are only guessing from the pattern. You have not proved it completely. So now this is an opportunity for you to apply induction and prove this completely. So prove that this is the formula. And importantly, when you are applying induction, you have to do two things. You have to prove the base step as well as the induction step. Okay. So suppose this is the question given to you, then the solution can be something like this. So we use induction on. So this is an important statement where every induction proof should start with this. You have to define what is the variable on which you are doing the induction. What is the index? In this case, it is t, which is going to go over all the natural numbers. Okay. So then the first thing is the base step. So the base can start from 0 or 1, doesn't matter. So we can start with 0 in this case. So in the case of 0, LHS is, RHS of star simply n minus 10 by 2 raised to 0 plus 10, which is equal to m. Which is true because that is what is given. So this is given to you, x0 is equal to m. We are just confirming it. Then we have to do the induction step. So given that star is true for some t, prove it for t plus 1. Which means what? We are given that this statement is true for xt. So given that xt is equal to m minus 10 by 2 raised to t plus t, then prove that xt plus 1 also matches the same formula. And what you are allowed to use is the recursion which is given. So this is also given. Okay. So in this case, it turns out to be very simple because you can just plug in the formula directly. So from here you can say xt plus 1, which is xt plus 10 by 2. And here I'll just substitute the value of xt which is given to me. So if I do that, I'll get m minus t by 2 raised to 10. Okay, so here I just took the denominator 2 on both sides. So here, if I divide this by 2 and this by 2, I'll get this. So this exactly matches what we have to prove here as required. So therefore, by induction, star is true for all natural numbers t. Okay. So if you were to write in the exam, if you just wrote the pattern that you were showing last time, that this is the pattern and therefore this is the formula, you will not get, I don't know if you'll get any marks, you might get a partial marks for guessing the formula correctly, but you will not have proved it. But if you follow it up with the induction proof that what you are showing is through induction that this formula is true for every natural number t, then truly the proof is complete mathematically speaking. Okay. Okay, so this is just one example of how induction can be used.
Yeah.
Yes, go ahead.
Sir, in the proof, I didn't understand according to condition 2.
The induction step, you mean?
No, sir, in the proof of the
Oh, in
mathematical
the
induction.
proof. Okay, okay. So see, where we use condition 2 was, what condition 2 says is that if some integer belongs to S, then the next integer also should belong to S. So what we did was, because we want to prove that this S has all the natural numbers, we said if possible, let there be some natural numbers which don't belong to S. Okay, and we put all of those elements in the new set T. So T is the complement of S. Okay, T has all the elements which don't belong to S. And then out of the all the elements of T, we took the smallest possible number, which was N. Okay? So N is the smallest value in T, which means that anything smaller than N cannot belong to T. Correct? So in particular, the number just before N, which is N minus 1, N minus 1 also does not belong to T, which means that it has to belong to S. And if it belongs to S, now here we can use condition 2, because what condition 2 says that if some number belongs to S, then the number after that, so N minus 1 plus 1, which is N, also has to belong to S. And that is a contradiction because N was taken in T, right? So T is the set of all numbers which don't belong to S. And now we are in a situation where N is belonging to S as well as T.
But
So
sir,
which
we
is,
have to prove that condition, right? The second one.
no, this is given. All of this is given. Given all of this, then S is the set of natural numbers.
Okay, okay, sir.
So one common illustration of this is what we call the domino effect. Have you seen this example like dominoes? So you can place dominoes side by side in a straight line. Such that if you knock the first domino, it will cause the second domino to fall. The second domino will cause the third domino to fall, and the whole row will fall that way. That is what induction is all about. We are going to knock the first domino, which means that we are saying it belongs to S. And whenever the kth domino topples, it will also force the next domino to topple, k plus 1 domino to topple. And so the what we are claiming is that this chain will consume the entire series of natural numbers. All the like this is infinitely many dominoes, and all of them are guaranteed to fall. That is what induction is saying.
Okay.
Okay, so I hope that the theorem, the induction as a theorem is clear, and how we can apply it in a problem is also clear. That here we used it to prove this formula, but you can do similar thing in other fields also. So maybe just to give you some problem for practice, something that you all know, I think. So we know what is NCR, right? N choose R is the number of ways to choose R elements out of N. So what is the formula for N choose R?
N factorial
N.
upon R, n minus R factorial times R factorial.
Okay. So I think you may already know one proof of this formula through counting, right? You know how to count, etc. But now I'm asking, can you prove this by induction? Prove this formula by induction.
So you have to prove this for all n or for specific n and all r.
You want to eventually prove this for all N and all R. How you approach it is up to you. So I want to prove this for all N and for all R. Oh, I should clarify that R cannot be greater than N, because otherwise the formula would not make sense, right? So for all N and for all R in the range 0 to N. Okay, so for all natural numbers N and all natural numbers R from 0 to N. Okay, so I want to point out one thing here, because there is both N and R. The question might be, what should you apply the induction on? Should you keep R constant and change N, or should you keep N constant and change R?
And
Yes,
constant.
Yes, so I think we should keep n constant because r is dependent on n.
Okay.
Actually, I was thinking the opposite way,
Okay.
that if we prove that for all r of this n, the condition is satisfied.
Yeah, I was thinking the same thing. Like we can take one value of n and then prove for all values of r, and
Okay.
then proceed. The base case would be n equal to
For
1, so
all
r
of
must
the
be.
n's for this condition, then
Okay. So as it turns out, we can use both approaches. But before we
one
get
thing we must
started,
take is that for
yeah, I mean, just a minute, just to show the illustration of what we are trying to do here. So this is actually two-dimensional induction in some sense, because both n and r are going to change over time. So on this, let's say this the horizontal axis is n and the vertical axis is r. Okay. So let me just show what are the pairs that for which we want to prove. So for example, of course, n equal to 0, we are going to ignore. So if n is 1, then r can be either 0 or 1. If n is 2, then R can be 0, 1, 2. If n is 3, R can be 0, 1, 2, 3, etc. So these dots which we are highlighting, these are all the ones which I want to finally cover. And you see this like a triangle will grow on the right side. This kind of a triangle. It's an infinite triangle on both sides. And eventually we want to prove this for all the points on this triangle. So there are two ways to do this. One is that you start with the horizontal axis. Okay, so you start with the base case on the horizontal line. So in general, the base case will be some value of n and r equal to 0. And from here you apply the induction to go to the upper case. So basically from n comma r, I want to prove the value through the formula for n comma r plus 1. Okay, this is one way to do it. So basically we are going to cover the lines vertically. You can also do this horizontally. You can start with the base case which is on this diagonal blue line. Okay, so you can start with the base case where n and r are both equal. And horizontally you will keep r constant and increase n. In that case, from n comma r, you will go to n plus 1 comma r. Okay, the point on the right. So both approaches are valid. The only difference is in what is the starting base case. If you do the vertical induction, then your base case is basically n is some value and r is 0. And if you are starting with the want to do the horizontal induction, then you have to start with n and r equal. That is the only difference, but both approaches are valid. Do you see that? I mean, both approaches will eventually cover all the points of interest, which is what matters to us. So, in fact, this is the challenge for you. Try to prove it in both ways. So, use induction in both ways. So, let's say first approach. Let us say we are going to use induction on n. R. So, first let's do induction on r.
And in the horizontal case also, we should additionally prove that it holds for r equal to n plus 1, because it will not get covered in the n choose r for r of n.
No, see, we are going to prove that this point is, we have to prove the base step anyway, right? So we are going to prove
Yes,
the
sir.
base step. And if any point is covered, then n plus 1 comma r is covered. So in that, inherently this point will also get covered, right? When we do the base step, we are going to do the base step for any value of r.
Yes, sir.
So does that resolve your question, or am I missing something?
No, sir. Like what I was saying, that if we are saying that if n choose r holds, then n plus 1 choose r holds, right?
Yes.
Sir, but in the n choose r, the restriction on r is that okay, sir. So that is covered in base step. You are saying.
Exactly. So when the same logic is applied for the row above, that will cover this point.
Yes, sir.
Okay.
Thank you, sir.
So we will use. Yes, go ahead.
So, won't we have to say that n choose means if our value of r is say n plus 1, we don't need to disprove that or anything, that it won't hold true.
No, I didn't understand your question.
So, do we need to also mention in the proof that if r value exceeds n, then the
Okay,
formula
okay.
won't hold true?
No, I think that's okay, because in the question itself, I'm restricting that r can never be exceeding n. Okay, so you can assume that r is always less than or equal to n. That is fine. Okay, so let us do vertical induction first, which means that we use induction on r. So which means that the base case to be proven is where for some value of n and r equal to 0, I want to prove that this formula is true. In other words, I want to prove that n choose 0 is n factorial upon 0 factorial by 2n factorial, which is 1. So is this base case true? If we want to choose 0 elements out of n, there is only one way to do it, which is we do nothing at all. Okay, the kind of question is redundant in some way. So So the base case is, it's actually very good that the base case is like this. We don't have to do anything at all. So in fact, this is one of the problem solving techniques that you learn, that you always try to choose the base case which is trivial. Okay? So we can just say this is trivial and we don't have to do anything in this case. Okay, now the induction step. So given that the formula is true for n choose r, prove that the next term n choose r plus 1 is given by and remember this n choose r, what it represents is the number of ways to count or choose r elements out of n. So how will you prove the induction step? So here one of the important ideas about induction comes into play is that we don't try to solve the problem from scratch. So to find the formula of n choose r plus 1, which means that out of n objects we have to choose r plus 1 objects, right? But what is given to us, we already know how to choose r objects. So we have to use that information somehow. We don't try to solve this as a fresh problem. So induction works very well when one big problem has another small problem hidden inside. So when you want to choose r plus 1 objects, first r objects you already know how to choose. So only thing left is that last r plus 1th object is the only one you have to choose, right? So what will happen? Yes, Anushka.
So first we can choose n r objects out of n objects.
Okay.
Out of n objects, and then out of the remaining n minus r objects, we choose one object.
Okay. So to choose r plus 1 objects out of n, first step is that we can choose r objects in n choose r ways. Now the next step is we will choose the r plus 1 object. So how many ways are there to choose the r plus 1 object?
N minus r ways.
N minus r ways. So then the answer is n choose r into n minus r.
Sir, but there will be a repetition factor.
Yes. Why will there be a repetition factor? Can somebody clarify?
Sir, can I?
Yes, go ahead.
Sir, like if you are selecting any three numbers out of 1, 2, 3, 4, 5.
Okay.
Sorry, yes, any three numbers, and say we are selecting 1, 2, and 3. So if
Okay.
in the first step, if we select if in the first step if we select 1 and 2, and in the second step we select 3, then we get the required collection. But in the first step we select 1 and 3, and in the second step we select 2, the collection is same, but they are counted differently.
Yes, sir. Adya, do you have the same idea or something else?
Yes, sir, same idea.
Same idea. Okay. Okay, does everybody follow what will happen? If I, in the general notation, if I say that let the objects chosen be denoted as x1, x2, xr, xr plus 1. So basically the same set of objects can be constructed into different ways, or rather how many different ways we'll see. That for example, it could be that x1 to xr were chosen in step 1 and xr plus 1 was chosen in step 2, and so on and so forth. So basically out of these r plus 1 objects, any one of them could have been chosen in step 2 and the remaining r objects will be chosen in step 1. But in all of the cases, we are going to get the same ultimate combination, which means that this particular choice is going to get repeated how many times?
R plus
R plus 1 times.
R plus 1. So therefore, in this following this method, each set of R+1 objects will get counted R+1 times. Therefore, you have to divide by R+1. So therefore, what is the formula for n choose R+1 that will get?
So I didn't get this part, the repetition one.
Okay, I think maybe best to illustrate with some numbers like what Arnav was saying. So suppose n is equal to 5, r is equal to 2, which means r+1 is equal to 3. Okay. So we want to choose 3 objects out of 5, and the way we are going to do it is in 2 steps. First, we are going to choose 2 objects, and then we are going to choose the third object. Okay. So for example, if the objects are A, B, C, D, E, okay, and in one of the countings, let's say we first choose A comma B in step 1, and then we choose C. So the set we are going to get is A, B, C. But in another order of events, maybe somebody chose A and C first, and then they chose B. See, the order doesn't matter. When you choose the object, finally they are going to go in the same set. So you see, the same set ABC can be constructed in 3 different ways. Whereas we only want to count the set once. So the number of ways to choose the first pair, which is 5 choose 2, into the number of ways to choose the second object, which is 3. This 5 choose 2 into 3 product is going to count each answer 3 times. Whereas, so the repetition factor is 3 here, therefore we have to divide this answer by 3, and we'll get the actual number of how many ways are there to choose 3 objects out of 5.
Yes.
Okay, do you follow? And you see this in this toy example, of course, this is true because 5 choose 2 is equal to 5 choose 2. Okay, so the same thing we are doing here. So n choose r+1, it will be basically n choose r. And by the way, this is multiplication principle, right? Because we are going to do step 1 and step 2. So it is what is the answer of step 1 into step 2. So n choose r into n minus r and divided by the repetition factor, which is r+1. Okay, so once you establish this, it is just a matter of plugging in what the induction base gives us. The n choose r formula we already know. So what is n choose r? N factorial into okay. So you will see how these factorials are going to absorb these terms. So what will happen? The n factorial in the numerator will remain the same, but in the denominator, this r factorial is going to combine with r+1 and will get r+1 factorial. At the same time, this n minus r is going to get cancelled with one term from n minus r factorial, and you are going to get n minus 1 r minus 1 factorial. Okay, so this is n choose r+1, and this is exactly the same formula which we are expected to prove. Okay, therefore by induction, the proof is complete. Okay, did everybody follow how? So here we did vertical induction. If I go back to my diagram, so here we started with the base case on the horizontal x-axis. So we started with n comma 0, and from n comma r we went to n comma r+1. Okay, can I leave this exercise to you to prove the other way, the horizontal direction from n comma r? How do you go to n+1 comma r? Okay,
Sir, I have a
so
question in this proof.
sorry.
I have a question in this proof.
Okay, tell me.
Sir, in the induction step, we wrote that the given n choose r is equal to n factorial upon r factorial n minus r factorial.
Yes.
Do we write something like r is less than n, because if r is less than or equal to n, then r+1 may not make sense. N choose r+1.
Yes, I think that's a good point. So here we have to assume r is less than n.
Because
See,
here we have
anyway,
a final case.
yeah, if r is equal to n, then there is no further step to be done. It is the end of that induction. That's a good point. Okay, so I hope you can try this at home, how to do the induction on the horizontal axis. Quite similar argument, just the counting will be slightly different.
So sir, we have to perform induction on n right now.
Yes, you have to perform induction on n keeping r constant. So what happens if you have one more object to choose from? Okay, in fact, let's do it right now. I mean, it's not, it's good that all of us go through the steps here itself. Okay, so now this was proof 1. So now let us look at proof 2. So now we'll do induction on n. So now importantly, the base case. So when you are saying induction on n, the base case is not r equal to 0, but r equal to n, right? So n choose n is the what we want to prove. Again, this is trivial because how many ways are there to choose one object out of n objects out of n objects? There is only one way where you choose everything. So the base case is again trivial. Okay, and now the induction step is that given. So now we can assume r is greater than equal to n, and n choose r is the same formula. Prove that for n choose r plus 1.
So n plus 1 choose r.
Oh,
N,
sorry.
Sir, induction on n.
R less than or equal to n.
R is negative. Yeah. We want to prove that n plus 1 choose r. N plus 1 factorial upon r factorial n minus r plus 1. Okay, so the base step is already done. We have to prove the induction step. So again, as I said, this is an example where we have to find out how to reuse the smaller part to solve the big part. All of us know how to select r objects out of n. How can we use that to select r objects out of n plus 1?
So I think I'm done.
Who is speaking?
So Sarva.
No, I cannot see you on the screen. Who is speaking?
So Sarva.
Sarvam. Okay, yes, tell me.
So in this there are two cases.
Okay,
We either will choose the n plus 1th object or we won't choose the n plus 1th object.
right. Correct. So let's say case 1 is we choose the n plus 1 object.
So
Then
if
what will
we do
happen?
choose the n plus 1th object,
Yes.
then we have to choose remaining r minus 1 objects from remaining n objects. So n
Yes.
choose r minus 1.
Okay, so then we have to choose n choose r minus 1 objects to be chosen. Okay.
In case 2, we don't choose the n plus 1th object.
Okay. Then what happens?
If we don't choose the n plus 1th object, then we have to select r objects from the remaining n objects. So that is NCR.
N. Okay. So therefore, what do we get combining these two?
So we add NCR and NCR minus 1.
Yes, I think everybody knows this identity, Pascal's identity, right?
Yes,
Yes.
sir. Yeah.
Okay. But the big question is now, we want to find a formula for n plus 1 choose r. The induction base step only gives us the formula for n choose r. What about n choose r minus 1?
We are indirectly doing the vertical induction.
So do you see that to do this induction, we need the, here because we are doing horizontal induction, which means that while r is constant, we can change the numerator. But here when the r is itself changing into r minus 1, then we cannot use induction.
Yeah, got it.
So we'll have to divide NCR minus 1 also into some way subpart.
Okay, or you can use what I mentioned earlier, what is called a strong induction. Okay, what strong induction is that here we just assume that this formula is true for n and r. In strong induction, we can assume that this is true for all smaller values of r also. Okay? So, in other words, in the diagram, when we are doing the induction of this particular line, we can assume that everything below it is already done. Okay. So therefore, in that r minus 1 is also covered. Okay. Are you following this? So strong induction gives us more information to work with. It is not just that this is given, also given that so for r less than equal to n, and for all. So typically, what we use is some other variable k. So for all k less than r also, we can say n choose k is equal to n factorial upon k factorial n minus k. Okay. So pictorially speaking, if the current row on which we are doing induction is r, then any row below that from 1 to r, so k can be anywhere in between. So that row is also given to us. Okay. So in this case, for example, we wanted just the row before that, r minus 1. So in some example, you may require multiple rows before that. Okay, but here r minus 1 is sufficient. Okay, and now you can substitute everything and do the induction. Okay, I will not do the algebraic calculation. I think everybody can manage that. Okay, but do you see how we both require the normal induction as well as strong induction in some cases? Okay, so I'll encourage you to go back and by the way, for number theory, this book is highly recommended. Elementary number theory. Burton. So Burton is a very famous author. So this particular book is gives you all the required theory for Olympiad, and actually a bit more than that also, but at least Olympiad theory is covered. In particular, I think chapters 1 to 7 are what we are going to cover, and which is sufficient for RMO and even INMO also. Beyond chapter 7, there are some topics which are, if you are liking number theory and interested, then by all means you should read all of that. But as purely problem solving tools, chapter 7 and actually maybe chapter 8 also, primitive rules. But this is the sort of foundation of all the number theory that we are going to study. Okay. So you will find lots of practice problems in this book, and do spend the time to solve. Almost entirely we are going to follow the same order that Burton does, except a few changes which I feel are strongly required. So in particular, the theory of congruences I do before prime numbers, but otherwise it's almost the same order. Okay, so I think we covered a couple of examples of induction, and particularly you saw how there can be non-typical ways to apply induction also, because the standard induction is you go from n to n plus 1 on a straight line. But here you saw that how on a 2D plane there will be multiple orders in which you can cover the whole area. There can be even more sort of complex ways to cover all the numbers. In particular, there is one proof of Amg inequality, which I think is very illustrative in this way. So, does everybody know what is the Amg inequality?
Yes, sir.
Yes.
Yes.
And does everybody know proof of Amg inequality?
Yes, sir.
Sir, I know for two numbers.
For two, okay. So basically, yeah, for two numbers, if a and b are given to be, sorry,
You just subtract them and write it as a square.
yes. So a plus b by 2 is greater than or equal to root a. So a plus b by 2 is the arithmetic mean, root a is the geometric mean, and what AMGM says is that the arithmetic mean is always greater than or equal to geometric mean, and with equality only if they are equal. So this is for two numbers. What about more than two numbers? Do you know the proof for 3, 4, 5, n numbers? So the more general Amg inequality is let a1, a2, an be all non-negative real numbers. Then the arithmetic mean of all of them, that is the average, is greater than the geometric mean. Okay, again m greater than 0. And again equality only if they are all equal. Okay, this is a very important inequality in Olympiad algebra questions. So there are multiple proofs of this. One of them uses a very funny induction, and that is what we are going to look at. So to begin with, here we did the AMGM for two numbers. Can you see how to apply AMGM or rather prove the AMGM for four numbers? Yes, Gaurav.
Yes, sir. So first of all, the expression would be like this, that a plus b plus c plus d by 4 should be equal to fourth root of a, b, c, d. So this is
Yes.
what we have to prove.
Yes.
And so we can assume it like in two particular steps. That so it is, yes, sir. So so don't consider a b c d, just okay. So we know that a plus b by 2, a plus b by 2 is greater than equal to root ab.
Yes.
So we consider two cases.
Okay.
That we take it as root ab by root ab plus root cd whole divided by 2.
Okay.
And yes, and then we try to solve that means.
Yes. So basically, first we do the level 2 in AMGM. So at the level 2,
yes,
we have a plus b by 2 greater than root ab and c plus d by 2 greater than root cd. If we add these two inequalities themselves, and by the way, you can always add inequalities, but you cannot subtract them. So what you will get is a plus b plus c plus d whole by 2 is greater than root ab plus root cd. And now you have to apply AMGM to this itself. So we'll divide everything by 2 once again. So we'll get a plus b plus c plus d by 4 is greater than equal to this by 2. And now you see I can apply AMGM of level 2 once more, and this will be the square root of these two. So it will come out to be the fourth root of ABC.
Yes.
We are applying AMGM to root AB and root CD, right?
Yes, correct. Okay, so we first applied AMGM to AB and CD for these two, and then when we added them, we are going to apply AMGM to root AB and root CD. So do you see if I can continue this chain from 4 to 8 to 16 to 32? In general, if let's say we will talk about 2 raised to n. So let us take 2 raised to n numbers. So a1, a2 up to a2 raised to n be real numbers and all greater than 0. Okay. And given the AMGM inequality is true for this, so given that given AMGM of level of level 2 raised to n is true, prove that AMGM of level. So when I say level, it simply means the number of terms. Okay. So given AMGM of level 2 raised to n, can we use that to prove AMGM of level 2 raised to n plus 1? Okay. So suppose I have 2 raised to n plus 1 numbers like this, a1, a2 up to a2 raised to n plus 1. Then what I can do is I can split them into two groups, right? So first group is a1, a2 up to a2 raised to n, and the second group is a2 raised to n plus 1. A2 raised to n plus 2, a2 raised to n plus 1. So these are two separate sets of 2 raised to n objects each. And for by the induction step, because this level 2 raised to n induction is given to me, I can use that on the first set and the second set. So what will I get? A1 plus A2 plus by 2 raised to n is greater than or equal to the 2 raised to nth root of the product of all of these. For the first set, and for the second set, I'll get the same thing, right? A2 raised to n plus 1. Yeah, writing this is very tricky. Okay. So having applied two AMGMs of level 2 raised to n, what we can do, we can add them now. So when I add them, the LHS will get added and RHS will become another AMGM of level 2, correct? So if I add these two, and I have to divide everything by 2 again. So I'll ultimately get A1 plus A2 plus A2 raised to n plus 1, whole thing upon 2 raised to n plus 1 is greater than or equal to 2 raised to n 2 raised to nth root of A1, A2, A2 raised to n plus 2 raised to nth root of this second series. Upon 2, because we are divided by 2. And now I can apply MGM of level 2 to finally get what I want.
Strong induction, right?
But do we need strong induction here?
For level 2 we need.
Oh, I mean, in level 2 you can assume is given, because level 2 we did. I mean, you can use it not as part of the induction chain, but as a fundamental property.
Okay.
So level 2 induction, you can level 2 MGM is given as a sort of standalone statement for us.
Okay.
But of course, you can call it under strong induction also. There is nothing wrong with that. Okay. So this is how from AMGM of level 2 raised to n, 2 raised to n, we can go to level of 2 raised to n plus 1. Okay. So this is a power of 2 kind of induction. Okay. So from 1 we go to 2, we go to 4, to 8 and 16 and so on. But what about the terms in between? Like we still have to prove AMGM for 3, for 5 to 7, and all these terms in between, right?
Sir, if 3 is proven, then 6 is already proven, and then the other
Yes,
numbers will means other even multiples of 3 will all all multiples
that's,
will be proven. Sorry.
that's true. But then we'll have to do it for 5 and 7 again separately.
We'll have to do it for all primes.
So that is, I don't know if somebody can come up with a proof like that, that will be brilliant. I don't know that way. I'll suggest a different approach. See, this 1, 2, 4, 8, 16, this pause of 2 will keep on going all the way up to infinity, right? So the idea here is actually to backtrack. So from, let's say you want to prove for any number between 5 and 7, can we use the starting point as the level 8 AMGM? So can you think of some way of applying the level 8 AMGM to prove AMGM for any of these intermediate terms, 5 to 7? Even similar example, just to prove for 3, can you use the level 4 AMGM to prove the level 3 AMGM? Okay, so what you want to prove is that given, let's say numbers a, b, c greater than equal to 0, prove that a plus b plus c by 3. This is what you want to prove, and somehow you want to use level 4 AMGM. So see, what we know is level 4 MGM, and let me use some different letters. So let me use x plus y plus z plus w upon 4 is greater than 4th root of x, y, z, w. This is what we are allowed to use to prove this.
I think we use some special numbers like 0 or 1.
You're right. You have to use special number, but not 0 or 1. Some other special number.
Sir, we can say a plus b plus c upon 3 is some k.
Okay.
So k will be equal to a plus b plus c plus k upon 4.
Correct.
And then use AMGM of 4, I mean x plus y plus z plus w upon 4.
Okay.
And then we can come to the inequality of 3.
Okay. So let k be equal to a plus b plus c upon 3. And so what you are suggesting is let us apply AMGM of level 4 on a, b, c, and k. Correct? So if
Yes.
we apply MGM for these 4 variables, what happens? The LHS becomes a plus b plus c plus k upon 4 greater than equal to 4th root of a, b, c, k. So we all agree this is true because we are assuming the level 4 MGM is given. Now can you see if this can be somehow simplified into this? Okay. We'll let everybody try. So just to illustrate why this was a natural choice, right? Why did we think of this k? The reason being, see, k is the only number which you can add to the set of ABC without changing the average. You see that if you are given some numbers and you take the average and you just add the average as one more element to the same set, the new set has one more extra element, but the average has not changed, right? So therefore, I mean, through calculations you will realize that, but this LHS is exactly equal to this LHS. So LHS is exactly identical. So only the RHS we need to manipulate. Gaurav, you want to say something?
No, sir, I was trying to say the same thing, that a plus b plus c plus k whole divided by 4 is equal to k.
Yeah, exactly, correct. So, I mean, see, we have to think about the motivation. Finally, this question is not going to get asked in Olympiad at all. But the reason why we chose this special k and this kind of like hidden variables are there many times, means you have to guess level. So here k was that variable. Okay, so what will happen? So here LHS is nothing but a plus b plus c plus a plus b plus c upon 3 whole thing upon 4. And when you substitute this, it will be 4 by 3 and the 4 will get cancelled. And we'll be left with a plus b plus c. Okay. And the RHS is 4th root of ABCK. This 4th root of ABC into a plus b plus c by 3. What do we do now?
So therefore we can say that a plus b plus c whole divided by 3 the whole raised to 4 to a plus b plus c by 3 into ABC.
Sorry, can you repeat that?
So we remove the radical sign. So therefore, so just if you could just keep it as k.
Okay, okay. Okay.
Yes, sir. So therefore, k raised to 4 is equal to ABCK.
K raised to 4 is equal to ABCK.
Yes, sir, because LHS is equal to a plus b plus c by 3, which is nothing but k.
No, but this is an inequality, right? We can say k raised to 4
I'm,
is,
I'm sorry. Greater than. I'm sorry.
okay, okay. So k raised to 4 is greater than ABCK, correct?
Yes. So therefore we can reduce k.
Yeah, so we'll get k cube greater than ABC, and therefore k is greater than cube root of ABC.
Yes, sir.
Okay, I'll just repeat for everybody. So we got LHS is a plus b plus c by 3, which is nothing but k, and RHS is fourth root of ABCK. So what we know is LHS is greater than or equal to RHS, which means that in other words, k is greater than fourth root of ABCK. And what we now want to do is just cancel out one copy of k from both sides. Okay. So you can do it directly also, or see, we want to retain one copy of k on the LHS. If you just cancel out k, then on the LHS we will be left with nothing. So before we do that, if you just take out the radical, we'll get k raised to 4 greater than ABCK. Now we'll cancel one copy of k, and we'll get k cube greater than ABC. And now if I again take the cube root of both sides, I'll get k greater than cube root of ABC, which was the level 3 AMGM we wanted. So you saw how from level 4 AMGM we went back to level 3 AMGM. And there was nothing special about the numbers 4 and 3. Can you see how in general you can go from level n AMGM to level n minus 1 with the same technique?
Yes, sir. Like that, we can
Yes,
go
sir.
from 8 to 7, 7 to 6, and 6 to 5. So 5
Exactly.
are proof.
So you see how this is a very funny induction, because we started with powers of 2. So from 1 to 4, 8, 16, any power of 2 you can reach. And from that power of 2, you have to backtrack from, let's say, from 32 to 31, 30, 29, like that. But in this complex scheme also, you see that all integers will be covered eventually. All natural numbers will be covered. Okay. So what I'm trying to show is that there are so many different creative ways to apply induction, not just linear that go from 1, 2, 3, 4 up to n. So like we are just seeing 2 or 3 examples today, but over time you will come across so many examples of induction, and that will build your sort of intuition that okay, which kind of induction should you apply where.
Sir, can you one k is greater or equal to fourth means root of ABCK?
You want to explain this step?
Sir, can you explain that? Means I did not understand.
Okay, sure. So see, what we did was we defined that k equal to a plus b plus c by 3, and we know the level for AMGM is 2. So we applied that for a, b, c, and k. Okay, so therefore this statement is true that the AM of ABCK is greater than the GM of ABC. And now we are just simplifying what is the LHS and what is the RHS. So do you agree that the LHS is nothing but equal to k?
Yes, sir.
Okay, so therefore LHS is what I wrote here, and the RHS is I've just copied it exactly like that. Okay, so therefore k is greater than fourth root of ABCK.
Yes, sir. Got it.
And after that, the manipulation were just simply to make sure that we get the form of level 3 AMG. Okay, so I'll encourage you to go and look at the David Burton book. I think it's a pretty old book, so it might be out of copyright also. You might get a easy like a PDF online or something.
I have a soft copy of that. Burton.
Okay, so I'll just check if I also have that, and I'll share it to the group. Otherwise, I'll ask you to share it. And if you also want physical copies, then you have Bhaskaracharya Pratishthan at Law College Road. You can go and get their library membership, and they will have plenty of copies of the book. Again, to repeat the name, it is Elementary Number Theory by David Burton. Okay. So in some sense, what we covered today, like well ordering principle and induction, these are the most basic facts about integers as such. Most of the number theory is related to things such as divisibility, GCD and LCM, congruences, prime numbers. So all of those things we are going to get into from the next lecture onwards. But many times we use induction to prove some things or well ordering principle. So these are like you can say the foundations of the number theory, which is going to come next. Okay. So I have around 20 minutes left. Actually, it's not enough to start any new topic as such. So I think why don't we continue with the puzzle that we had talked about last time?
Yes,
So,
sir. I was able to reduce the number to 501.
501. Okay.
Sir, I
Then
reduced it till 64.
64. Okay. Anybody else? We started with 1000. See, everybody agrees 1000 prisoners will be sufficient. But how lower can you get the number? That's the whole question. So let's start in any question like this.
I guess it is 10.
Yes, sir, 10.
Okay, so many people are saying 10. And I think somebody also posted their solution, but I'm not fully convinced about what is their logic. So let us give everybody a chance to get at that answer. Okay, let's start with a smaller example. And this is something you should always do in Olympiad problems, that if you are presented with a big problem, try to find a very small construction of the same problem. Okay, well, I think he has sent a book to everybody. Okay, so in case you don't get it, you can just ask somebody to share it. So always try to construct the simplest version of that question. Suppose there are only 2 bottles and one of them has a poison. Then how many prisoners will you require to solve that problem?
1.
1.
1, right? Because you will give the bottle to one prisoner, just 1 drop, by the way. And if he does not die, then the other bottle is the culprit. Okay. So if we can make a table here, that number of bottles and the minimum number of prisoners required to solve the problem. So in the case of 2 bottles, 1 prisoner is enough. What about, let's say you have 4 bottles. Okay. So suppose you have 4 bottles, let me call them bottle 1, 2, 3, 4. Or in fact, I'll start the numbering from 0. Okay. So bottle 0, bottle 1, bottle 2, and bottle 3. So how many prisoners will you require? Anybody who has already got the answer, can you tell me? 2. Okay,
Yes.
so let me call it prisoner 0 and prisoner 1. And so what is the idea? Who will you give which bottle?
The first prisoner, the P0 will be given bottle 0 and bottle 1.
Okay.
And P1 will be given bottle 0 and bottle B0 and B2.
B0 and B2. Okay. So what will happen now?
So if both of them die, then bottle 0 has the poison. If
Yes.
P0 dies, bottle 1 has poison. If P1 dies, bottle 2 has poison. And if nobody dies, bottle 3 has poison.
Correct. So do you see, in general, if you have 2 prisoners, how many different combinations of who dies and who does not die are there? 2 raised to 2, which is 4, right? In effect, what I'm asking is that if I give you a set of 2 elements, how many distinct subsets are there? So how many subsets of this are possible? So the answer is 4. So the idea is that every subset should lead to a different conclusion. That if nobody dies, in this case, for example, if nobody dies, then the answer is B3. If only the first prisoner dies, then the answer is B1, and like that. Do you see that every possible combination of who dies and who does not die leads to a different answer in terms of the bottles? So if you appreciate this idea, then so the answer for 4 is 2. Can you see how this will be generalized? Suppose you have 8 bottles, then how many prisoners will you require?
3.
3.
3, right? Why? Because if you have 3, if you have number of prisoners, so if I let P be the set of the prisoners, so P0, P1, P2, then I think this standard problem everybody has done, right? How many subsets of P are there? The number of subsets of P will be 2 raised to 3 because P has 3 elements. Because basically every element has 2 choices. Either you pick that element or you don't pick that element. So 2 into 2 into 2, 3. And so all those 8 choices should be assigned to different bottles. So maybe if nobody dies, then the bottle 0 is the culprit, and so on and so forth. So the whole question is, how do you construct this table systematically? So this table which we are showing here. So in the small example like this, you can easily do the tick marks, that which bottle is given to which prisoner or not. But in a larger example, how do you construct this systematically?
Sir, we can use binary notation.
Yes. So that is the main hint here. So that is why I started numbering from 0 value, 0, 1, 2, 3. So the idea is actually, so this is a whole topic that we are going to do in number theory, okay, which is called base representations. That just the way we have decimal representation, any number can be represented in any finite base. And in particular, binary numbers have some very nice properties which we can exploit. Okay. In particular, what you can do is, so any natural number can be written as a sum of distinct powers of 2. Okay. So any natural number, for example, in the case of our original example, which was 1 to 1000, right? So every number like 2 raised to, take the number 50. So how can I write 50 as the sum of some distinct powers of 2? So 50 is like 32.
2 raised to 5 plus 2 raised to 4 plus 2 raised to
Plus
2 is
2,
to
right?
2 raised to.
So see, the number 50 can be written in terms of 2 raised to 5, 2 raised to 4, and 2 raised to 1. So what you can do is you can give bottle number 50 one drop to prisoner 5, 4, and 1, like that. So basically, whatever combination of prisoners dies, that will tell you exactly which bottle was poisoned. And in general, if I write down the binary numbers for the initial few values, you will see the pattern. So the fundamentally how binary numbers work are exactly how the decimal numbers work. In decimal number system, we have a concept of place value, correct? If I have numbers like 432 or 437, then we call the units place, tens place, and the hundreds place. So any digit which comes in the units place is basically being multiplied by 10 raised to 0. Any digit in the tens place is getting multiplied by 10 raised to 1, and the hundreds place is 10 raised to 2. So like that, the power of 10 keeps increasing with every place. And when you add up all of this, you get the actual value of the number, which is 4 into 10 raised to 2 plus 3 into 10 raised to 1 plus 7 into 10 raised to 0. And each digit can be in the range 0 to 9. So in the same way, so this was the decimal notation. And the reason why decimal notation became popular is because we have 10 fingers. But imagine that there is some alien who has only 2 fingers. So they will use binary counting system. So in the binary counting system, every place represents a power of 2. So the first place is a power of 2 raised to 0, 2 raised to 1, 2 raised to 3, etc. And every digit now can either be only 0 or 1. So for example of 50 that we just saw right now. So because we can write 50 as 2 raised to 5 plus 2 raised to 4 plus 2 raised to 1, which means implicitly all the other coefficients are 0. I mean, I could also write this as plus 0 times 2 raised to 3 plus 0 times 2 raised to 2, etc. But that is understood. So if I want to represent 50 in binary, I have to write 1 in these 3 places. Okay, so 110010 is the binary representation of 50. Okay, does everybody follow this? And so basically any number can be converted back and forth from binary to decimal. Okay, so typically the notation used to indicate what is the base is you write it as a subscript. So when I write 437 bracket and a small 10 below, which means that this is a number being represented in base 10. So in that way, what I can write is 50 in base 10 is the same as 110010 in base 2. In common notation, we don't write the base 10 every time because it's kind of understood by convention that almost always we are talking about base 10. But in some problems, you might see that we are dealing with different bases. Then this kind of notation is quite common. Okay, so I'll leave it for you as an exercise to discover how to convert a number from decimal to binary and vice versa. Important thing to say is that even addition, subtraction, multiplication, and division also works perfectly well in binary base. Okay, there is nothing special about decimal number system. You can let's multiply two numbers in base 10 as well as base 2. So let us say 11 into 7. the answer is 77 in base 10. If we convert the numbers into base 2, so 11 in base 2 is what? So 11 is 8 plus 3, right?
3 plus
8 plus 2 plus 1.
1011.
So 2 raised to 3, 2 raised to 1 and 2 raised to 0. Correct?
1011.
So it will be 1, 1, 0, 1. Okay. So this is the, in the decimal system you call units place, tens place, hundreds place. Here you have to call it units place, twos place, fours place, eights place. Okay. And what about 7?
1, 1, 1.
1, 1, 1. So by the way, very important thing to note. In the decimal number system, what is the largest 3-digit number you can write is 999. Where after that, you have to start with the new place. In the same way, in the binary system, any power of 2 minus 1. So 2 raised to 3 minus 1 is 7. Or 2 raised to 5 minus 1 is 31. So 31 will consist of all ones. And after that, the next number 32 will be 1 followed by number of zeros. Okay. So same thing happens here also. Okay, so this is 7. So let us multiply this in binary notation. So let's do it in the traditional way where you have to do it one digit at a time. So first row will write multiply 1 with the number above. So that is simply 1011. Next place we have to add a 0 and multiply with 1. Next place we'll add 2 zeros and multiply. And then we'll add all of this. So when we add the first column, the answer is 1. Second column, what is 1 plus 1?
2, but that will give us 10.
0.
Yes, in binary 1 plus 1 is 1 0, right? So 1 0 means 0 and 1 carried over. The third column is 1 plus 1 plus 1, which is 1 1. So 1 and 1 carried over. Again 1 carried over. 1 plus 1 is 0, 1 carried over. So 1 0 0 1 1 0 1. Can you check if 77 in base 10 is this number in base 2? So this is 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 5, 2 raised to 6. So this should be 2 raised to 6, which is 64 plus 8 plus 2 plus 1.
64 plus 13.
Yes, it is coming out.
Yes, sir.
So 4 plus 1.
So just as you know, Einstein had his theory of relativity that there is no preferred frame of reference. In that way, we can have our own theory that decimal system is not special. Same thing works just fine in binary, ternary, any base system, it works just fine. And we'll study this more properly in the when we do this topic in number theory. But
8 plus 4 plus 1?
Yes, sir.
Oh, sorry, 8 plus 4 plus 1. Okay. But see, I mean, how flexible these systems are. And in fact, binary numbers are going to be the basis of many ideas to come in the coming days. Okay, so many puzzles, many games will be based on binary numbers quite often. I hope this bottle question is resolved completely now. So do you see why 1,000 prisoners require 10,000 bottles require 10 prisoners? Because the largest power of 2 after 1,000 is
102.
102.
10 is 1024. Which means that if you have 10 prisoners, then all possible 2 raised to 10 sets can be represented in this way. And each combination will lead to a different answer. And also, do you see why less than 10 prisoners will not be enough? Suppose you have only 9 prisoners, what will go wrong?
Maximum outcomes possible are 5 and 2, but those won't be enough to test all the 1,000 bottles.
Yeah, exactly. So when you have 9 prisoners, see, every prisoner is either going to die or not die. So the total number of possibilities 2 into 2 into 2, 9 times, which is 2 raised to 9. So 2 raised to 9, which is 5 and 2. So you can distinguish among at most 5 and 2 distinct possibilities. And if you are given 1,000 bottles, then there is no way you can cover all the bottles in that. Okay.
So what I thought right now was if the prisoner number 1 dies, then if any prisoner dies, we write 0 in that place, and if it is alive is 1, then the number forms we get the binary representation of the bottle number.
Yes, that is correct. So let's say we can illustrate that in a small number. Let's say we have 8 bottles and 3 prisoners, and let's make the table that which bottle is given to which prisoner. So what we can do is we can just write prisoner 0, 1, 2 list like this, and let's write out the bottles here. So this is bottle 0, bottle 1, bottle 2, etc. So first thing we do is every number. So here 0, 0's binary representation is all zeros. So which means that 0 means we don't give that bottle to that prisoner. So bottle 0 is given to nobody. Then bottle 1 is given to only prisoner 0. Like that we can fill out the whole table. Okay. So in every place 1 means that we give that bottle to that particular prisoner. Okay. And now see what will happen. Suppose only prisoner 2 dies and prisoner 0 dies and prisoner 1 survives. Then can you tell me which bottle has the poison?
So bottle 5.
Bottle 5, because this means that prisoner 2 was given the poison, prisoner 0 was given the poison, and he was not. So from this number you can convert this number itself into decimal, and that will give the answer 5. Or you can look at the table. Okay, and the same system can be used for even 1000 prisoners and 10 bottles. Okay. So in fact, this points to a heart of how computing works. If you know anything about how computers work, they represent all the information in binary. So all the numbers or text that are forwarded over the internet, all of them are converted into some binary form and then transmitted and then decoded back. So in particular, can you tell me the English alphabet has 26 characters, right? So 26 letters. If you want to send them as binary, how many binary digits will you require? How many bits will you require?
5.
5.
5, right? So for 5 bits will be sufficient, but we also have capital and small and all of those variations. So in fact, we have punctuation marks, we have the digits 0 to 9 and few other things also. So in all, as it so happens, all the sort of common characters combined turn out to be around 256 symbols. So we require to send typically 256 various kinds of symbols from one person to the other, or even when you are saving a document, if you save a Word document or a text file, you require 256 distinct symbols. So how many bits will you require for that?
8.
8 bits, right?
8.
So
Yes.
8 bits are enough, and that is why 8 bits together are called 1 byte. So if you have done any study in any computers or anything like that, you of course come across the word byte. So 1 byte is actually 8 bits. And so that is how it became sort of the fundamental unit of all discussions related to computing. Okay, so the 1 byte, which has 8 bits, and we'll see in the future that we can be smart and we don't always require full 8 bits to represent 256 symbols. We can be clever and use a less number of bits to represent the same information. In fact, that is how compression works. That whenever you create a zip file, typically the zip file is much smaller than the original document, right? How is that possible? So that is possible because of you can represent the same information in a different way in the binary number system. So we will look at all of that also in one of the future games. But I think we are almost out of time. So one last thing to mention is that about the puzzles that everybody, or rather the problems that everybody is constructing. I hope you are taking some time to look at each other's problems also. Okay, because there are some very nice ideas there. So you are going to increase each other's problem solving capability in that way. Okay, and I'll also keep adding my own puzzles to the collection. So we'll keep growing it over time. As I said, I also have some feedback in particular for some questions which you may have designed. So I'll contact you directly for that. Okay. I think that's all for today. Thank you. Bye.
Thank you.
Bye, sir. Thank you,
Bye,
sir.
Thank you, sir. Excuse me, sir.
So we can start watching the videos from your channel about the geometry last year.
Yeah, I think you can start watching them, and as I get time, I'll try to edit them and sort of polish them a little bit. But even if whatever the form they are right now, you can just watch it. Maybe if there is a pause, you can just fast forward it. In fact, use that pause time to try the problem yourself, like just the way you are attending the lectures. And in that, one thing which will not happen is we won't be interacting directly. But for that specifically, I will conduct a few, one of these sessions, I'll have like a problem solving discussion on those topics. Okay.
Sir, no puzzle for next time?
No homework for next time. I'll send you some homework on the WhatsApp group. Okay.
Yes.
Okay. Thank you. Bye.